Okay, so today I'm going to talk about RubyGems and RubyWasm. This year, we have made significant progress in RubyWasm, and I'm excited to share the latest status with you. By the way, this year we have 4 WebAssembly talks at this Kaigi. I'm happy to see the expansion of the WebAssembly community in the Ruby community. And if you are interested in WebAssembly, please check out the other talks as well. And also, let's make Ruby more WebAssembly friendly together. So, let me briefly introduce myself. I'm Yuta Saito, a master's student at Watson University. I'm newbie committer of the C Ruby and Swift, and especially working on WebAssembly support for both languages. And I'm also the creator of RubyWasm. And today, I will start with a brief introduction of RubyWasm itself, and the challenges of RubyGems support on RubyWasm. Then I will show you a demo. After that, I will explain how we support RubyGems. Finally, I will share the future vision and roadmap. First of all, RubyWasm is a project that enables running Ruby on everywhere by WebAssembly. Note that everywhere is not limited to web browsers, but also runs on edge computing platforms, embedded devices, and also as a plugin system. The project consists of the 3 main components: C Ruby interpreter compiled to WebAssembly, and a packaging system for Ruby files, and an interrupt library for JavaScript. The main component I will focus on today is the second one, the packaging system for that packages the interpreter and Ruby files. Let's see how it looks like. This is an example of running Ruby on web browser using RubyWasm. You can run Ruby code in a script tag in an HTML file. And also, you can access DOM API. And you can await JavaScript promises using await method, so you can write asynchronous code in a synchronous way in Ruby. And this is an example of running Ruby on standalone WASI runtime. Thanks to its portability, you can run Ruby on various platforms outside of the web browser, such as Docker, NGX, fast-rate compute, Shopify functions, and more. Okay, so we can run Ruby code on WebAssembly, interact with JavaScript, and run on various platforms. But what about RubyGems? How can we use RubyGems on RubyWasm? As you know, RubyGems is one of the most critical components in the Ruby ecosystem. And RubyGems has 2 main components. The first one is gem installer, and the second one is a runtime loader. The runtime loader is something that enables loading installed gems at runtime. The loader itself is already supported from early version of the RubyWasm. So you can use required gem name as expected, even on WebAssembly. But as of the last year, only default gems and bundled gems are available due to the lack of the gem installation support. RubyGems has 2 types of installation methods when thinking about WebAssembly use cases. The first one is on-the-fly installation, which installs gems at runtime. The second one is pre-installation, which installs gems in advance before running the Ruby program. On-the-fly installation is a convenient way for daily scripting. Effectively, it runs gem install command on WebAssembly. So it requires network access at runtime. And this on-the-fly way is similar to PyOdido's micropip, which is a Python package manager for WebAssembly environments. This is technically not so difficult, and I showed a demo at RubyKaigi 2022. Network access can be passed through the browser's fetch API, and Soviet Lab made a good playground for it. But we haven't added first-class support for the on-the-fly installation yet due to network traffic concerns. And due to the network access requirement, it's not available on some platforms like edge computing. So we are focusing on pre-installation support. So pre-installation is another way to install gems in advance before running the Ruby program. It does not require any network access at runtime, but it requires a build step before running Ruby. You can run gem installs on the host machine, then package the installed gems into the WebAssembly binary by virtual file system. And currently, we can use on-the-fly installation for pure RubyGems, but we don't have first-class support for it. And also, C extension gems is not available on the fly. And we didn't have any support for pre-installation as of last year. So in this talk, I will focus on the pre-installation support for both pure Ruby and even C extension gems. So let me show you a demo for the gem support. This demo shows the quality of the gem support, and okay. So we have a static files. There is no dynamic process here, and just serve them by HTTP server. Open it Chrome. Loading, booting. Wait a second. Okay, let's launch. Okay, it works. As you know, Mastodon is a large-scale Rails app, and it works on inside browser. You may think it's crazy, but it's real. And you can log in the server. Note that it's localhost. Log in. Let's create a post. Okay, it works. So Mastodon runs inside browser. Okay, it works. So it's a quite large Rails app, and it includes many gems, including C extensions. So it's a good example to show the quality of our gem support. It's a backup run. So actually, I was thinking about showing a very simple Rails app a few months ago, but Parkan from Evil Martians already did it for a few months ago. So I decided to bring something new for you. So please note that this is too extreme and just to show the quality of our gem support. So I don't know even know if it's practically interesting, but it was just quite fun, at least for me. So don't take it seriously. And this is the architecture of the demo. The Mastodon app is built on top of many gems, including Nokogiri, Hamo, Active Record, and many more. Some of them, like Nokogiri, includes C extensions, but we can now run them on the WebAssembly. The Rails app runs on Service Worker, and it intercepts network requests from the web page. Then the app responds those requests through Rack interface. The app runs Postgres inside the browser too, and it communicates with Active Record, so it have ephemeral storage inside the browser. So even as I said, it's a demo just for a demo, but I'm thinking that hosting Rails app as a static site might be practically interesting. In this way, we just need to deploy the static site to HTTP server or S3. So if we can easily run Rails app as a static site, we can create a low cost and low security risk environment easily. This might be useful for preview environments for prerequisites, but I don't know actually. So let me explain the technical details of the RubyGems support on RubyWasm. This is the main part. There are three main topics I will cover today. Packaging gems and putting cross-compile C extensions, putting C extensions shared libraries. The first one is the easiest thing. We recently added a new command, RubyWasm build, to our RubyWasm gem. The command packages gem sources listed in the gem files into the WebAssembly binary. The packaged gems are stored in the bundle directory inside the virtual file system. And you can set up the load paths by bundle setup as usual. Then you can require the gems. Nothing is special here, so the next challenge is cross-compiling C extension to WebAssembly. If you want to build C extensions, you need to talk with MKMF. As you know, MKMF is the core of the C extension build system in the Ruby ecosystem. And MKMF is an abbreviation of makefile, and it literally makes makefile from xconf.rb. Now we have three major users of MKMF. The first one is the C Ruby build system that uses it to build built-in extensions like string.io, JSON, YAML, and the Rake compiler also uses it to build gems while developing gems and building fat gems. And the last user is RubyGems. RubyGems uses it to build gems when you run the gem install command. CRB build system and Rake compiler already supports cross compilations. It's done by their bespoke RubyConfig toric, but RubyGems does not support cross compilation at all. The way CRuby build system and Rake compiler does is to override top-level RubyConfig constants and some of Ruby constants. This toric tells MKMF that the compilation target is different from the host platforms, but it does not work for some corner cases where the C extension needs to know the host platform at configuration time. And our extension in CRuby repository do not have such cases, and we can control their configurations script xconf.rb. So it's no problem, but it's not the case for the Rake compiler, and which is expected to be able to build any gems. And the Rake compiler has a workarounds for it. But this is a very specific corner case, and it's not a general solutions. And this means that we cannot generate this toric for all gems, and we need to address some of major issues by step by step. But it's not the ideal scenario. So instead of introducing a new toric to RubyGems, we introduce cross-compilation support to MKMF itself. The new option, target RubyConfig option, allows you to specify the RubyConfig file for the deployment target platform. The top-level constants are not overwritten anymore with these options, so it's more robust and general than the existing toric. This feature will be available Ruby 3.4 and later. And we are working on adding support for the new option to RubyGems. And it's still under review, but the demonstration I shared today is based on this feature, and it works. So we have we can cross-compile C extensions to WebAssembly, and we have cross-compiled library. Then next step is to link the compiled library to the C Ruby interpreter. We have two options for linking C extension to the interpreter. The first one is static linking. The second one is dynamic linking, as you know. So we have already supported statically linked extensions for built-in extensions, but we decided to go the dynamic linking to support RubyGems. Why? The main reason is that the build model is not suitable for RubyGems ecosystem. Static linking takes a long time at link step, especially async file, which is a code transformation applied after the linking, is quite slow. And also, we need to tightly integrate with the CRuby build system to support static linking. This is a comparison of the build model between static linking and dynamic linking. In the static linking scenario, it starts from configuring the CRuby build, but note that it tells where the C extension library will be located before the actual build. Then it creates a RubyConfig and some headers required to build C extensions. Then pause the CRuby build process. Then configure the C extension build, compile the C extension using RubyConfig and headers. Finally, resume the CRuby build process. In this way, every time we add a new C extension, you need to reconfigure the CLB build and wait for the slow linking step. On the other hand, in the dynamic linking, it's much more simpler, and we do almost the same thing on other platforms. It just configure and build the CLB, then it builds the C extension. That's it. So okay, so dynamic linking is the way we should go. But why we didn't go do it so far? The main reason is that WebAssembly does not have a standard dynamic linking API. If we do our bespoke dynamic linking as the Nscripten does, the produced binary will be incompatible with the standard WebAssembly runtimes. So we will lose the portability of WebAssembly if we do it. However, the situation has changed recently. The WebAssembly community has been working on a new layer of WebAssembly standard, the component model. The model is built on the top of the existing WebAssembly standard, and we expect it to be the future of WebAssembly. The component model consists of several features, including with IDL, module linking, and more. But the most important feature to achieve dynamic linking is module linking. Module linking is a new concept to build a program by composing multiple WebAssembly modules. The new binary format allows embedding multiple WebAssembly modules into a single binary. And also, it allows describing how the modules linked, how the module link is linked to each other. So based on the module linking, we can build dynamic linking mechanism on top of that. The key idea here is that given that each module has a metadata for dynamic linking, such as symbol table, relocation record, and which module it depends on. And we can encapsulate how to link modules into a new binary format. And we call it and in this way, in this case, we have 4 WebAssembly modules: CLB interpreter, string IO extension, Nokogiri extensions, and the libc shared library. Given those modules, the ahead of time linker wires them up and bundles them into a single component. The AOT dynamic linking is a little bit different from the traditional dynamic linking, and the actual linking is done at build time and not at the runtime. The final binary is a single component, and it contains all the dependencies. The linker itself was originally developed by Joel for Python on WASM, but I found it's also useful for Ruby as well. So I had been working with him and fixing issues and adding a new feature to satisfy our use cases, and it's now ready to use with Ruby. The main difference from the traditional dynamic linking is that the final binary is a component that contains all dependencies. So it's fully self-contained, and the linking is done at build time, so there is no file-based library search at runtime. Therefore, DL Open is available only for the library known at the build time. So it's not possible to inject new library at runtime. So we have pre-installation support for both pure Ruby and C extension. Some of the changes are still not upstreamed yet, but it will be available soon, so stay tuned. Okay, so finally, let me share the future vision and roadmap for the RubyWasm. This year, I drew a roadmap for my 3 goals. The first one is the binary size. You might have noticed that our binary is quite large, and such a large binary is not suitable for the web, and so we need to reduce it. The main bottleneck of the binary size is async, and to make it possible to have unstructured control flow in WebAssembly, async adds a lot of overhead to the binary. And also it adds overhead at runtime. Also, however, it requires getting rid of the async file requires some of new WebAssembly specs and changes in the instruction set, so it may take long, but I think this is the way we should go. And also, the other goal I'm thinking about is that making the WebAssembly to be more normal platform. Actually, the current status of the WebAssembly itself is not well normal. It does not require a good debugging experience, and the current WASI Preview 1 does not support good networking stack. So we should have many things to do. And also digging into the binary size, I made a rough outline of the interpreter size. Currently, the largest build is about 30 megabytes, and it's quite large, but we have several levels of optimization to reduce it. The information can be stripped without any trade-off in the most cases. And if we can sacrifice a little bit of the performance, we can apply further program size optimization at compile time, like function merging, outlining, and more. And to go further, we need to purge a part of the functionality, like extension library. And this is the current state of the art, but once we will be able to remove async file, we can step forward and we will get more smaller binary size. As far as I investigated, if we can we can make our C code more size friendly, especially like for big switch case in C, and also, we can even purge some of interpreter components to have minimal interpreter. I'm not sure if it can be practical, but or we need another approach, but I feel it's worth trying. So we have many things we can do this. We still have many optimization space here. So in summary, RubyGems support will be available soon on RubyWasm. And Ruby is leveraging the state-of-the-art WebAssembly technology, including component model. And we are investing the evolution of WebAssembly to make more WebAssembly friendly. So let's make Ruby more WebAssembly friendly together. Oh, wait. Finally, I would like to mention that this work is supported by the Ruby Association Grant Program and advised by Mame and Koichi. So thank you for your attention. That's all from me.